The pit stretches 3 miles across. At the bottom, 200 feet below the surface, exposed coal seam runs like a dark ribbon through layers of rock and clay. The overburden, the waste material sitting above the coal, has to be removed. Thousands of tons per day. Hour after hour, a dragline bucket swings into position. It's the size of a 3-car garage. The operator sits in a cab suspended from a boom so long it reaches halfway across the pit. He lowers the bucket. It descends on 4 cables, each one 5 inches thick. The bucket touches ground. The draglines pull. The bucket teeth cut into overburden. Material fills the cavity. The bucket closes. 150 tons of rock and clay in a single scoop. The hoist lines tighten. The bucket rises. It swings, a smooth arc that takes 5 seconds. The bucket dumps. Overburden cascades into a waste pile that's growing, yard by yard, ton by ton, every single day. The machine is a walking dragline. It doesn't run on wheels or tracks like shovels do. It walks. 4 massive feet, each one powered by electric motors, lift and step and pull the machine forward. It moves at a pace measured in feet per day, not miles per hour. But it moves. It works. It removes more material per shift than 10 shovels combined. This is the dragline era. Not the age of the shovel, not the age of trucks, the age of the dragline, the machine that defined American surface mining from the 1920s through the 1980s. The machine that removed mountains 1 bucket at a time. Before we continue, if this history matters to you, subscribe to the channel. Every video documents the machines and the men, draglines, shovels, the equipment that transformed American Earth. Did you work mining? Did family operate draglines or shovels? Grow up in coal country, Appalachia, Ohio, Wyoming, Kansas? Tell us in the comments. The people who worked these machines know stories that don't appear in company records. We want to hear them. Now, the machines. The dragline wasn't invented for mining. It was invented for dredging. In 1904, someone created the first dragline to remove sediment from rivers and canals. It was simple, a bucket suspended from a boom on cables. The bucket was dragged across material, filling with soil or sand, then lifted and dumped elsewhere. Mining companies watched. By 1910, the dragline appeared in American mines, but these early machines were crude. They worked, but they were slow. The real breakthrough came in 1913, when a Monican engineer named Oscar Martinson invented the walking mechanism. Instead of being mounted on fixed rails like shovels, the dragline could walk. 4 legs, each one powered independently. The machine could position itself, work for hours, then pick up and walk to the next location. This changed everything. By the 1920s, draglines were removing overburden at coal mines across Appalachia. By the 1930s, they were standard equipment. By the 1950s, they were massive. Bucyrus Erie, Marion Power Shovel, and P&H were locked in competition to build bigger machines. The Monacan walking mechanism became so iconic that miners called all draglines Monacans, regardless of who built them. The name stuck for decades. Every coal company wanted one. Every major mining operation deployed them. They were the workhorses of surface mining. After World War II, American coal demand exploded. Electric utilities were building power plants. Steel mills needed coal for heat. The post-war suburban boom meant houses being wired for electricity. All of it required coal. Strip mining became the economic answer, and draglines became the machines that made it possible. In the 1950s, dragline sizes doubled. Marion introduced the 8950, a machine with a 150 cubic yard bucket and a 310-foot boom. Bucyrus built draglines that could move 500, 600 tons of overburden per day. P&H competed with machines of equal scale. The competition drove innovation. Bucket designs improved. Walking mechanisms became more reliable. Operators learned to push machines harder, faster, longer. By 1960, a large dragline working a coal mine could remove overburden covering an entire coal seam in a single shift. The economics were simple. Fewer machines, lower operating cost, higher production. A coal company with 2 draglines could supply a power plant that served 50,000 people. The machine had become essential to American infrastructure. The 1960s and 1970s were the dragline golden age. This was when Big Muskie was built. This was when Ursa Major entered service. This was when the machines reached their absolute peak in size and capability. The engineers and manufacturers weren't just building equipment anymore. They were building monuments to industrial ambition. Big Muskie wasn't built because mining needed it. It was built because engineers wanted to see if it could be done. In 1967, Osiris Erie began construction. The Central Ohio Coal Company ordered a dragline that would push the absolute limits of what mechanical engineering could achieve. One machine, one bucket, remove more overburden than any dragline ever built. It took 2 years to construct, over 200,000 man-hours of work. The machine arrived on 300 railroad cars. Assembly took a team of engineers more than a year on site in Muskingum Mine, Ohio. When it was finished, Big Muskie stood 22 stories tall. It weighed 13,500 tons, equivalent to 2,500 elephants. The bucket was 220 cubic yards. 2 Greyhound buses could fit inside with room to spare. In a single scoop, Big Muskie could pick up 325 tons of overburden. Its cables were 5 inches in diameter, thicker than a man's leg. The boom stretched 310 feet. The walking mechanism moved the machine forward on 4 massive feet, each powered by 250 horsepower motors. Big Muskie dug its first bucket on a June morning in 1969. It worked for 22 years, from 1969 to 1991. In that time, it removed enough overburden to expose coal seams that generated electricity for millions of homes. At peak operation, Big Muskie consumed as much electricity as a town of 27,000 people. They ran it at night when power rates were cheaper. But Big Muskie was a victim of its own scale. The machine was too big, too much downtime for maintenance, too expensive to operate as coal prices fell and environmental regulations tightened. When it was retired in 1991, attempts to sell or preserve it failed. The cost of dismantling and moving such a machine was astronomical. In 1999, Big Muskie was cut into scrap. Operating a dragline was different from operating a shovel. The dragline operator didn't see the bucket directly. He saw it through a system of mirrors and windows. He worked from a cab suspended hundreds of feet above the pit floor. One mistake, an overcrowded bucket, a bucket hitting the pit wall, a cable jerking, could break a machine that cost millions of dollars. A dragline operator needed precision, timing, understanding of how the machine responded to cable tension, how overburden would move and flow, how to position the bucket for maximum efficiency. A good operator could remove 10% more material in the same shift than a mediocre operator. 10% was money. Significant money. Dragline operators earned middle-class incomes by the 1970s, $50,000 to $75,000 per year for experienced men. But the work was dangerous. The machines were powerful. They were also mechanical. They failed. Cables broke. Walking mechanisms got stuck. If an operator didn't respect the machine, it would kill him. The largest draglines required support crews, electricians who understood the massive electrical systems powering the walking mechanism, cable handlers who maintained 5-inch diameter cables under constant tension, hydraulic specialists, welders, mechanics. A dragline wasn't operated in isolation. It was part of an ecosystem of specialized workers, each one trained to a specific task. By 1985, the dragline era was ending, not because the machines stopped working. They worked until the day they were retired. But because the economics had changed. Environmental regulations tightened. Coal prices fell. The cost of operating a dragline, especially a giant like Big Muskie, became unsustainable. Hydraulic excavators arrived in the 1980s and 1990s. Smaller, more flexible, cheaper to operate. They could do what draglines did, but with lower fuel consumption and maintenance costs. Bucket wheel excavators, German machines that could remove material continuously rather than in discrete scoops, proved more efficient for certain applications. The dragline didn't disappear, it adapted. Modern draglines still operate in Australian coal mines and American surface operations. The Ursa Major still works at Black Thunder Mine in Wyoming. Newer P&H models work in coal fields worldwide, but the era of building draglines bigger and bigger, the era that produced Big Muskie, that era ended. The coal removed by draglines between 1950 and 1990 powered American electricity generation during the Cold War. It fed steel mills. It kept lights on in homes and factories. The overburden these machines removed is now reclaimed land. Some of it has become wildlife habitat. Some has been reclaimed for other uses. Some sits as monuments to the scale of 20th century American mining. The largest draglines ever built will never be matched. Big Muskie was unique. The engineers and designers understood they were building something that would never be needed again. It was ambitious. It was excessive. It was exactly what American industrial engineering of that era represented. A belief that scale and mechanical power could solve any problem. If this is the kind of mining history you want to keep watching, subscribe to the channel. There are more machines, more mines, and more operations still to document. And if you have a connection to what you just watched, a family member who worked in a coal mine or operated a dragline, someone who was there when these giants moved mountains, tell us in the comments, what did they operate? Which mine? What do you remember about the work? The people who ran these machines are aging now. Their stories matter. We want to hear them.